Okay, so there's all the lines, and so you know, you have to really dig down. For some reason they're white. I think you can probably change the color of these, but you can see, you can right click on those and it'll show you the duration of the message, the message size. You can see here it tells you, you can look at which processor it's coming from. This is a little bit hard to see with this particular color, so you probably have to fiddle with that. So it shows you the tag on the message. I don't think it shows. You can sort. It's kind of hard to see exactly where those begin and end because they're on this light background.
Yeah.
So, but anyway, that's something you can play with, and you can see which where the message is going to and from. Now, I think to get those lines, so if you look at, I think it'd be worthwhile to just take a quick peek at. So this tau cheat sheet that I mentioned. So I think to get those lines between all the messages, you have to enable an environment variable at runtime called, there it is. So this is, like I say, this is gold if you're going to work with tau. So you want to use tau _ track _ message. And this will, actually this is nice for tracing or profiling, because if you enable this, when you do profiling, it will track your MPI message statistics. So like what is the size, like the average size of your messages, and I don't know, I'm not sure all the statistics it'll track, but that actually could be very useful for tuning, say, your MPI parameters at runtime. They have different defaults for different message sizes, and so it might be interesting to look at. I know that NAMD, I fiddled around with. NAMD is kind of different than most MPI codes, and it sends lots of short messages. And in particular on Ranger, by tuning some of those MPI parameters, the scalability of NAMD increased by like 30%. And so I haven't found that to be the case for other MPI codes that use more traditional type messaging. But for your particular application, it might be worth looking at what the message sizes are and checking out some of those MPI parameters you can tune, because the performance benefit can be substantial if it's in certain cases. So anyway, so you can check out these runtime variables. But if you want to track MPI statistics, then enable that. Set that to 1 before you run the code. Okay, other questions? If there's not...
Bill, you did...
Yes.
One question. You didn't have to do any translation on that trace file, did you? That was the native trace file that you got out of Tau?
No, the actual... I've got the files, I think, on Queen Bee here, but the actual output is... Yeah, I did have to run a few commands. Actually, here it is. I'll just show you here. It shows you exactly how to do that in this cheat sheet. So what you'll end up with is a bunch of files like .edf and .tautrace and a bunch of stuff. So I actually did have to do translation. So this is the sequence right here for using jump shot, and it will vary for different other trace tools. But you have to run this Perl script here. This is all part of the Tau distribution. Okay, so this Tau tree merge. And be warned that these spit out a lot of stuff to standard error, so you might want to redirect that when you run it. Tau _ tree merge, and then you do this tau to slog2 on the resulting files from that, which will be these two files. And then here's your final file that you actually run to jump shot. So again, this little cheat sheet is very handy.
Thank you.
Sure.
So online or maybe in the Google groups, could we get access to the parameters and things you did to get that speed up for NAMD?
The NAMD speed up parameters are, yes, there's a number of places that I can post. I will post that to the Google groups. It's also on the NAMD wiki, and it's also on the advanced support benchmarks page in the example scripts for Ranger. And I can point people to all of those sources. Before we cut off here, there was an example that I wanted to show, and I'll run through it quickly. But since the focus of all these petascale machines is multi-core, I wanted to show an example of a code that really has shown impressive scaling and performance speed ups by using hybrid programming. So the question is, let me get to my. The question is, when is it worthwhile to make the effort to try to do hybrid programming on your code? And in the past, my experience had been that the modern MPI implementations really use efficient shared memory aware methods for doing the intranode communication. So it's pretty fast. And most of the time, in the past, I saw that hybrid implementations were either slower or only as good as the pure MPI implementation. So I always wondered, when is it really worth it to try a hybrid implementation of the code? And so here is one example of when it's worth it. And it sort of comes down to using this hybrid scheme to create balance between in your code. So this has to do with the example is LAMPS, and specifically a new version of LAMPS. LAMPS is a very good, efficient MPI code for molecular dynamics. It's very scalable, uses a scalable algorithm for the short-range communication, but lots of MD problems need to do long-range solve for long-range interactions that require a communication-intensive all-to-all, in addition to the short-range part, which is the biggest computational burden. Recently, someone had someone noted that the communication-intensive all-to-all is a computationally pretty much insignificant region of the code. Well, this has been known in MD codes for a long time. But the idea for LAMPS was to use threads in the computationally heavy region of the code to reduce the number of MPI tasks, and hence to reduce the amount of communication that has to be done during this all-to-all. And so this has recently been implemented in LAMPS by Axel Kohlmeier, who's at Temple. And there's a website where he has his sort of cutting-edge version of LAMPS available. It's experimental, be warned, but he does really good work. And I've been playing with this, and I thought for this workshop it would be nice to just show an example of a real production code that really rocks in hybrid mode. And LAMPS does that. This is the performance on Ranger. And at 1,000 cores, it's 4 times faster than the pure when you're running just one thread per task. So this is the results for 4 MPI tasks per node and 4 threads per task in the hybrid model, and versus just pure 16 MPI tasks and 1 thread per task. You pay a price at the lower core counts. Because there's a little bit of overhead associated with doing the threading, and also probably the bigger part is that those 4 threads are only active in the main part of the code, the computation. So some parts are being done in serial, whereas with MPI it's all parallelized. So So only certain sections of the code are parallelized with OpenMP. So at low core counts, you take a hit. But once you start to scale out and communication starts to dominate, then the hybrid strategy really pays off. And I just want to show that it's possible to profile these hybrid codes with Tau using, like I showed you, that Tau makefile that has OpenMP and Opari and MPI. And so here's some results that